talk about today is really suitable for the lithium-ion battery development. Obviously, there is a lot of changes, so it's not strictly lithium-ion. There's a lot of new technologies. I was at the battery show in Novi, Michigan, and listened to some talks. So there's a lot of new things that are coming down the pipeline where this equipment is really suitable. So ideally, we want to select the right type of dispersing and milling technology to give you the best homogenized product with the smallest particle size desired for different formulation and requirements. There is also obviously the need to narrow down exactly what technology you're going to use, because there is so much variety out there on the market. And we, for example, offer, the standard DISMATs, high-speed dispersers, but they can also function as media mills. So we have some customers that are using horizontal bead mills, but we have a lot of customers in that field that also use now basket mills, which are very attractive because of their ease of use and also simplicity to maintain versus the horizontal bead mills. We also have different vacuum dissolver options. It's always important to remove the air and maybe, put in an inert gas, argon, or anything that can be added with a special port in the cover of the machines to give you a vacuum and then flush it with a special inert gas. So we offer all these different solutions. Probably if you go on our website, you'll see a lot of different products, but that's only a small portion of what we do. 40% of everything that we design and VMA manufactures is customized. So there is a lot of things that we do, especially for this new industry where a lot of solutions are customized. So here you can just briefly see, and you're probably familiar with the growth potential. It's going crazy. See where we are today, where we were, a number of years ago, and where we'll be in the next 8-10 years. We can really see it's growing leaps and bounds. So there is also the need for new technology and different ways of doing things. So the DISMATs, basically dispersers, they have the trade name, VMA owns the trade name DISMAT, and they are known to make high-end dissolvers, bead mills, basket mills, for the development of these battery solutions, and also many other industries where that equipment will be used. Coatings, for example, 3D print media. We do a lot with ink manufacturing, cosmetics, but basically today we are gearing these presentations towards the battery and renewable energy market. So you can see all these different end-use markets or product areas where this equipment is currently used to disperse silicone and all these other components that you can see. I don't need to name them all, but that's what we use the equipment for. So basically we start out with a dissolver, which is a high shear mixer, very quick RPM, high RPMs and high tip speed. And that allows us then to develop the electrolytes, the anode cathode slurries. They are critical components in our battery. And then also we are able to add a basket mill onto the same equipment that allows us then to properly mill the particles. And we talk a little bit about that. I have some examples, the carbon black, for example, and other parts that are in these electrolytes where we're able to mill down these particles very efficiently. We use horizontal media mills to develop the separator coatings. That has to be done because we require really small particles sizes for most applications. So we're talking less than 100 nanometers. So there would be a need for a horizontal media mill. And then we want to also have the right equipment if we want to go from the lab space all the way up to manufacturing, that we have good scalability. And our equipment, we'll talk about that with the C technology, is designed to give you the exact values that you need to replicate what you would be doing in a lab space all the way up to manufacturing. So here we have a brand new piece of equipment which was introduced. This is the DISMAT AE renewable energy, and then we also have a VL version for renewable energy. That's a vacuum system that we are showing you right here with an integrated TMS or Twerk measurement system. The Twerk measurement system is great because it gives you real-time live Twerk measurement, very high resolution, 0.1 nanometers, that will give you live viscosity during the dispersing or milling process. So this is very important for a lot of different applications. As you disperse or mill, you want to know, hey, where is my viscosity and how is my viscosity changing? So in the past, and some other manufacturers actually calculate that value with the frequency inverter, but it's not very precise. So for that purpose, we actually developed that TMS sensor that we are now adding with these new Dispermats for the battery market that give you very accurate measurement of the torque in 0.1 Newton meters. And we're able to display that data live on our control panel. And you'll also see the actual torque curve over time. So that gives you a good glimpse of what's actually happening inside of the container while you're dispersing or milling with respect to the viscosity of your material. So that is really good. It gives you excellent repeatability and reproducibility, and it is not a calculated value. Again, it's a measured value. So here is an example of the Dispermat that we are using to develop a cathode. So here are just some of the ingredients that go in. We have the carbon black PVDF, NMP, the active ingredient, and then basically we use a high shear dispersing blade, and we're able to set up the new Dispermat either with a certain amount of speed or tip speed, but we can also run it with a certain amount of energy. Let's say I want to run this with 1,000 watts of energy, then the machine, depending on the viscosity, during the dispersing process will automatically adjust the speed to depending on what the viscosity state is. So if I, let's say, maintain my 1,000 watts of energy and my viscosity is increasing, that means my speed would now decrease because I'm maintaining the 1,000 watts of energy. If my viscosity decreases, my speed would increase because I'm having constant power and I'm maintaining that 1,000 watts of energy. That will now allow you to precisely also calculate how much it would cost to manufacture X amount of product in a certain time, because you know exactly how much energy you would be using on a lab scale, and you can basically use that data to upscale that to a manufacturing process. So that's really good with that C technology that we have with our higher Dispermats, what you can see right here. Here is an example where we had a cathode slurry development. We used the CN Dispermat, which is kind of a middle of the range model. We first pre-dispersed with the cowls blade for about 1 hour. We started at 100 microns. And then what we did after 1 hour, we swapped out the cowls blade and we attached a basket mill onto the CN20. That's that modularity I was talking about earlier, where our Dispermats are fully functioning, dispersing as well as milling systems. So we added a TML1, which is a basket mill, and we milled for about 3 hours. And then we were able to get down to 2 microns on average in the 3 hours of milling time. So the beauty is that it worked flawlessly, and the customer really appreciated the fact that the basket mill was very easy to clean. It took maybe 10 minutes, and then before they were using horizontal medium mills, which would take hours to take apart and then clean properly to run the next batch. So that was a huge advantage for the customer to use a basket mill instead of a horizontal media mill. So the next part here, we'll talk more about the different equipment. I want to talk a lot more in depth about the actual dispersion process of what we are really trying to do when we disperse and mill and what's actually happening. So you look at this picture, you see these larger blocks. I call them building blocks, but these are basically particles that are basically attracted to each other through these invisible forces. They're called Van der Waals forces. They're basically invisible magnetic forces. And they attract these primary particles to these larger clusters called agglomerates. And what we want to do is we want to break up these binding forces, and we want to reduce the agglomerates down to the aggregate size. And we can do that with the standard dissolver using a Cowles blade and a high tip speed. We're talking here probably 18 to 25 meters per second would be an optimized tip speed window, where that would then allow us to de-agglomerate and bring these larger particle clusters down to the aggregate size. If we want to go from the aggregate size down to the primary particle size, we no longer have enough shear force with the standard Cowles blade. That's when we need to start the medium milling process, which can either be what we showed you earlier, the basket mill approach, or with the horizontal bead mill approach would also get us to a vertical bead mill, like a so-called pot mill. That would also be an option to get us down to the primary particle size really efficiently. So this slide here is really nice because it kind of shows you exactly what is happening. So we are first, again, to pre-disperse, use the Cowles blade. That's the first part of the dispersion process, to actually de-agglomerate these agglomerates, turn them into aggregates. And at that stage, we are also wetting our raw materials that we are adding into our slurry. And after we've done that, we actually start the grinding process that allows us to really bring down the aggregates to the primary particle size, where after the milling process, we then stabilize our particles so they don't flocculate back together and stay in a suspended state. And for that purpose, we also need the right additives that our sister company, BYK Additives, can provide for the battery market. So here is an example. Unfortunately, there is a video that I'm not able to play it for whatever reason, but basically we're trying to show you here the DISMAT ARE, how we process some material, and using the basket mill that's attached here to the unit, and actually dispersing that material and milling it down to the primary particle size. In this case, it's a carbon black. And the additive that was used to stabilize the material from BYK was Laponite RD. And this basically, I'm not a chemist or an additive specialist. I would refer to my colleague Aaron Kelly at BYK Additives. But this ingredient is basically added to our formulation to basically improve the properties of our slurry and make it a more a processable material. So this is an important slide because it kind of shows us at what point are we starting to mill. So we always start out with the dissolver. And at that point, when we reach about 10 microns of particle size, usually 10 to 30 in that range, that's when we can start the milling process. So to allow us to get into the low micron range, submicron, and all the way down to super small nanoparticles that are very important when we develop our separator coatings, ceramic coatings, then we want to have a really small particle size. And for that, we need to have a good milling system to get us there. So predispersing, again, 18 to 25 meters per second tip speed. We'll use the cowl's blade on our dissolver. So we have a range of different dispermats. And for fine dispersing, the second part of our dispersion process, fine dispersing, milling, or grinding, as some people refer to, our rotor speed or milling disc speed is going to be 10 to 16 meters per second. And again, we have a variety of different milling systems. We can utilize a vertical bead mill, a basket mill approach, or if we really need very, very small particle size for separator coatings that they're like, we need to use a horizontal bead mill. The threshold usually on a basket mill with the standard setup is about 500 nanometers. That's about as low as we can go with the basket mill. With the horizontal mill, we can go much lower, sub 100 nanometers. We also offer vertical bead mills called the milling system APS, stands for air pressure system. We'll talk a little bit more later on, but that basically also allows us to get down into the very small nano range by utilizing that equipment. It's more for lab space. It's not really scalable, the APS system. So the maximum volume that we can do with this particular equipment is about 5 gallons. So it's kind of like the threshold. If we need more volume and or scalability, then the vertical bead mills are not really suitable. So you need to go either with the horizontal or basket mill approach. When we are dispersing, the first step, it's always important to remember that we want to use or have the right diameter, the ratio of our blade to our container size. And not one blade fits all containers. So you can see that chart on the right will kind of give us an idea of what kind of blade diameter we should be using. So let's say we have a 2-liter, 2-quart container. The 60 millimeter blade is kind of in the middle. As our viscosity is increasing, we can use a larger blade diameter. So if the slur is very thick, then it's okay to increase the diameter of our blade, and we can go all the way up to an 80 millimeter blade. If the viscosity is very low, then we can also reduce our blade diameter, and we can go down all the way to a 40 millimeter blade if we were to use a 2,000 milliliter container. Ideally, it's always, if the sweet spot usually is about 1/3 the diameter of the container should be our blade size. But again, depending on the viscosity, you have some range, and you can change out the blades depending on those values. This is really important, and I will share the presentation, but you may want to write this one down. This is actually the tip speed calculation. Some people, talk about RPMs and as the defining number, and that's only one variable. So the actual important value is how fast is my blade spinning, which is the peripheral speed. So the calculation is right here. So it's pi times the diameter of my blade, also times the RPM of my unit. If you want meters per second, you would just divide everything by 60, and the diameter would be expressed in meters. So if you have a 50 millimeter blade, for example, you would express that as 0.05 times, let's say, 2,000 RPMs times 3.14, and then you would divide all that by 60, and that would give you the actual tip speed that you would be running at. And again, when we predisperse, we want that number to be between 18 to 25 meters per second to optimize our predispersion window. Then we have something called the donut effect. it's really called that because when we look inside of our container, we actually want to see when we properly predisperse the formation of a donut. And that's what that looks like. So it's not really telling us that for different viscosity ranges, whether you're always properly dispersing. It's just kind of like the visual cue that we get if we are optimizing everything. We have the right viscosity range. We're talking here between 3 to 5,000 centipoise, and you optimize the tip speed window, you should see that donut. Then you know you're actually doing a good job predispersing. But and we'll show you some slide afterwards, you can still predisperse if the viscosity is very high or very low, and you may not see a donut. So we'll talk about that in a second here. But here you can see how the donut is formed by optimizing my blade speed, and then the teeth that are on my cow's blade on the edges are actually causing that shearing effect that will tear up these binding forces or break up these van der Waals forces that then will basically turn these larger agglomerates into the two aggregates. And that's what's really happening. On that picture here, I would add that same effect is also happening below the blade. It's not shown here on the graph, but you would also have the same effect below the blade, and obviously on both sides. So, but just to give you a visualization here of what's happening and what that looks like. So in this example here, we have an optimized dissolver prepared batch. We're running at 21 meters per second. We are putting in 850 watts of energy, and you can see a donut appears. It looks pretty good. So we know, hey, it's doing its job. We're properly de-agglomerating our material. Well, what's happening here is we are putting in 21 meters per second of tip speed. We're running 21 meters per second tip speed, but we're only putting in 320 watts of energy. What happened here is our mill base, the viscosity is too low. So that means if I'm increasing my formulation to bring up the viscosity, then I'm able to put in more energy, and that energy is used then to break up the binding forces. So to overcome it and create a good dispersion with that is either I can change the diameter of my milling disc, or I'm changing my formulation to add more energy to my process. I can also increase maybe my tape speed a little bit, or more time will also accomplish the getting a better dispersion result. And then we have a situation where if we have really high viscosity of our mill base, sometimes you don't see a donut at all. Doesn't mean you're not predispersing, it just means the viscosity is so high that a donut will not appear. And in this case, we are putting in a lot of energy, 900 watts, no donut shows up, means that the viscosity is very high. I can also change my blade diameter or adjust my formulation, but I would probably not see a donut in this case. Doesn't mean I'm not predispersing. So it's very important that we want to optimize our predispersion step. So usually we have to watch out for how much time we put in. Can be all the way up to 1 hour, depending on the slurry. We want to ideally see a donut effect if we optimize the viscosity and the blade diameter and speed between 18 to 25 meters per second. That's really important. The blade container ratio is very important. The type of blade, so there is a lot of different impeller blades on the market, some custom solution. So using the right impeller is critical. We have a really nice selection on our website, giving you good options to choose from. The amount of mill base, we usually want to work with about a 50% fill rate, 50 to 70%. We don't want to go higher because that would then mean that we probably spill the material when we put in the shear required to disperse the material. Or if we want to start milling with the basket mill and we have more than 70%, we also will probably spill material. The concentration of our additives is important. We want to cool our slurry. So when we are dispersing, we are putting in a lot of shear. Shear is translated to energy and heat. That means we also want to be able to cool our slurry and have double wall containers that give us that capability when we hook it up to a chiller. And then again, the right additives to have better wetting, dispersing effects, no flocculation once we're completed with our dispersing process, and then we can do the medium milling. So when we are milling, obviously we can put in a lot more energy. We then bring down the agglomerates down to the primary particle size. We are using media to accomplish this. So small beads will help us, break up these binding forces. We're able to put in a lot more shear stress into our slurry, and that will also give us improved characteristics of our material. The dissolver in itself is important. It's the first step, but it only is going to put in a limited amount of energy with the blade. It's only to de-agglomerate down to the aggregate level, not a real breakdown to the primary particle size. But it is a critical step for any dispersion process. So if you were not to use a dissolver first and you would go straight to a medium mill, potentially you would clog your screen or your dynamic gap, and you wouldn't have proper flow through the mill. And that is what we see a lot of times when customers want to forego that step and just go straight to a bead mill. So what actually is happening inside of our medium mill? So here is a great slide that shows you, as we have the two large beads inside of our milling chamber, and through the rotor and the shear that we introduce with the speed of our rotor, these beads start drifting and moving around in our slurry. So as these beads drift towards each other at high speed and actually collide, they are pushing away these larger aggregate clusters, and the aggregates get pushed away through that shearing motion, and that's what's causing the breakup of the Van der Waals forces, reducing the particle size as a result. So the goal here is not really to destroy the particles and cut them up, but to actually really break up the binding forces. Now, certain applications require that you are actually physically destroying pigment particles that you can achieve with the right bead size ratio, and also optimize the speed and everything and milling time. Then you can also accomplish that process. But most customers don't want to destroy the particles. They only want to break up the binding forces, and that's how that is done with the shearing motion inside of our milling chamber. Important formula here to calculate the kinetic energy. You may want to write that down. And then, as I mentioned earlier, beads are really critical. So obviously, the bigger my bead or the heavier my bead, not bigger, heavier, the higher my kinetic energy. And as you can see here on this chart, I can compare like glass to a zirconium oxide cerium stabilized bead. Obviously, the specific gravity is much higher on the zirconium oxide bead. You're also much harder, almost 3 times as hard. So we highly recommend that you stay away from glass beads and go always with zirconium oxide beads. The ceramic beads are much more durable, have way better wear. And the problem also with glass beads is that they break up and then you end up with shards in your slurry. So it's really recommended that you stay away from glass and always use good quality beads, zirconium, either cerium or yttrium stabilized. So I like this slide because it kind of shows where that shearing is actually taking place. So we have the larger beads, and then right in the corners as these beads collide, you have the particle cluster kind of wedged in between, but not really gets pushed away, and that then creates the shear motion to break up the binding forces, and you'll end up with the smaller particles as a result. And that's what actually happens inside of the mill. So there are some critical parameters that are influencing the bead milling process. So obviously, product temperature is critical. We don't want to get too hot. Milling is a very energy intensive process. So cooling is really critical. So we can cool our milling chamber, but also our supply vessel needs to be cooled. The particle size after we're done predispersing. Remember, we talked about 10 to 30 micron as a threshold. So anything smaller than that, we really need to start the milling process. Using the right bead size, enough milling time or residence time in our milling chamber, very important. How many passes I have going through. The specific gravity of our beads, again, stay away from glass, use ceramic beads. Bead volume, so there's always a range depending on what system you're using, that you use the right amount. The viscosity of the mill base is very important. Again, when we're milling, we want to have a good flow of our material. If we are too thick, it's going to impact the flow. And if, for example, we're using a basket mill, if it's too thick, we may not be able to process the material because it will not go inside of our basket and come out. So if it's viscosity is a big issue, then we would probably need to mill with the horizontal bead mill and some sort of a plunger setup that will actually force the mill base through the mill and kind of with the plunger create the pressure to force it through the milling chamber and then out. And then obviously the shape of the beads, they should always be perfectly spherical. So as you're using the beads over time, they will wear, and they usually wear unevenly. So it's very important that you screen the beads and then replace the fines that you're losing with new ones by weight. And then you just always add new beads to make sure you have the proper bead amount inside of your milling chamber. And then again, we are always trying to optimize our speed, and that is 10 to 16 meters per second when we are milling. And it doesn't really matter whether we are using a horizontal medium mill or a basket mill or a vertical bead mill. We always want to be between 10 to 16 meters. When we pre-disperse, that number again is higher, 18 to 25 meters per second. And then, as I mentioned earlier, there is different types of bead mills. So depending on how small of a particle size you want to get to, and whether it needs to be scalable, we have different types of bead mills. So I really like this slide because it kind of shows you the versatility of our DISMATs. So you start out basically with the standard DISMAT, and then you have the ability to accessorize it depending on your requirements. So you can either add a rotor stator, you can add a vacuum system, you can add a basket mill system, a TML, you can add a wall scraper system for really thick materials, and you can also add that vertical bead mill APS. So all these are modular accessories that will fit onto one machine. That really sets us apart from a lot of other equipment on the market, because you can buy one machine for many different application and end use requirements, rather than having to dish out the money for all these different types of equipment. You buy one machine and just buy the attachments as you need them. So This is a good example of the a battery slurry dissolver RE. So we have that Twerk measurement system I talked about earlier for very precise live viscosity measurement. We have the vacuum option. We have variable speed. We can run this machine with what we call the constant power, as I had talked about earlier, or constant speed. We achieve a maximum RPM of 20,000, so it's very high. That's required for very small volumes, and we always need to get to that right tip speed range that we talked about. Again, fully versatile with that quick change system to allow us to adapt to a basket mill or vertical bead mill by just removing that clamping ring, turn this assembly 180 degrees, and then you just pop on any of these other attachments. Very easy to do, very quickly. I can change from one system to another in less than 1 minute. And then we also have explosion-proof options. If you're running with a lot of solvent, or the installation area requires an EX version, then we have that option. The premium models come with software for you to store the data, look at the entire dispersion process in a graphical interface in real time. So each of these important variables, such as time, temperature, speed, torque, or energy, will also be displayed in a graphical interface. So you have basically a trend line for each of these values, that during the dispersing process, if something goes wrong, you will immediately see it, because you can see a peak or a drop in the trend line for each of these variables. So that's the C technology, really good for upscale, giving us a lot of that critical data. We have that capability for our lab, pilot as well as manufacturing scale equipment. Just briefly, our motors are all direct drive. They are brushless step motors. There are no belts. If you've ever worked with the DISMAT, you would recognize it immediately, that they are the most quiet machines on the market. Even at high RPMs, you can hardly hear the motor, and they have hardly any vibrations. I've been with BYK for 18 years, and I can tell you that I go on record, I've never seen one broken motor from the DISMAT brand. So that speaks volumes about the build quality of our equipment. So that here is that vacuum disperser, the VLFC. So that's actually a larger model here. That's a pilot scale model. Again, we have that also for lab and manufacturing. Here, what's great is you can see that it has the integrated wall scraper. We also have a dual shaft system called the LH, where you actually have two shafts, a larger and a smaller blade. But our wall scraper is so efficient that it almost functions as a blade, and it moves in the opposite direction of the direction of our disperser. So we're always properly pushing the material into the middle and getting a really good homogenized product. And the cover has a viewing glass. We can also add material while the unit is closed. And we also have the ability to add an argon purging valve or a nitrogen purging valve, depending on what type of inert gas you want to run. And you can create that blanket that you may want with that option. Again, very scalable, comes with the C technology and all the lab report tools and data recording options that come with the C technology. There are some videos on YouTube where we actually have examples of developing a battery slurry. If you go on there and you type in DISPERMAT VL, you can actually see some live videos of how the machine works and how product is added. Okay, then we have customers that have to operate more of the startups on a budget. We have the LC. It's a small battery slurry dissolver, just very simple, just a fast mixer, really, giving you the ability to control your speed and has a timer function, nothing else. Just very small volumes up to 5 liters, but also giving you that option to add a milling system if you want, or a rotor stator. So fully versatile, just like the big ones. We have the CV, which is basically a smaller lab scale disperser, giving you the ability to look at the torque value, which is in this case not with the torque measurement sensor, but a calculated value from the frequency inverter. Measures temperature, which is important when we are milling, and then also an electronic up and down lift motor. And it comes with the safety features of the container clamping system, as well as the H1, H2 height adjustment, meaning that the disperser will only run when the blade is inside of the container. So you can actually set a threshold point at upper and lower level, and then you operate within the 2 reference points. So if you were to lift up the dissolver while it's turned on, the machine will automatically stop at that upper reference point, avoiding any material gets splattered around the lab, or somebody getting hurt by a spinning blade. So that's what that is. And then we obviously have that clamping system that ensures that the container is always fully clamped. Then we have the CN line. That was part of an earlier slide that I showed you, where we used that and a TML mill to basically mill down a cathode slurry. Again, brushless step motor, super quiet, fully versatile, scalable, and again, speed, torque, temperature, timer function, just a little bit bigger than the CV line. Then we have the CN Advanced for pilot scale. Same technology, just larger containers. Then we have the AE premium line. This is also a tool with the C technology if you want to upscale. Again, constant power, constant torque. We can also go up to the next model size in the pilot range with the AE model. I'll show you. We have explosion proof models available. And then again, data storage, data extraction, upscale capability, and that modularity to turn it into a basket mill or vertical bead mill or rotor stator, all on one machine. Same model here, except for upscale in pilot, and then the next level up would be for production. With the pilot model, we can go up to 31 gallons of mill base. Again, we can have that as a vacuum system or with an integrated wall scraper system, depending on your requirements. We also offer a range of horizontal media mills. So we have the DISMAT SL, which is a lab scale dissolver with a nano kit that allows us to really mill down particles below 100 nanometers. Very efficient, perfect tool to develop slurries or separator coatings. Any project where you need really, really small particles, that is an excellent R&D tool. Again, C technology allows you to seamlessly scale up to manufacturing, where then we have the DISMAT RS, which is a large-scale production horizontal media mill. Can do up to 1,000 liters per hour on the large model. We have obviously some that for smaller volumes, but the top model, 1,000 liters per hour. So a lot of product can be produced with this machine. Fully ceramic, required for batteries. We don't want any metal bleed in. So we have that ceramic option, the nano kit vacuum option, ideal for the development of the separator coatings. And again, we also offer this model with an explosion-proof setup. Then we have production scale dispersers. Here we have the DISMAT SC, allowing us to go up to about 2,000 liters. We have made them larger on a custom basis with that quick change system, allowing you to go quickly from a dissolver over to a basket mill. So we also offer that combination system. And with the optional vacuum upgrade, if you don't want the air in there and you want argon gas, we have that capability there as well. Then here is the slide showing you just that quick change system, go from a dissolver over to a basket mill. Again, we have that ceramic option in our basket mill, so it's a very quick and seamless swapping of these accessories, I call them, and we also can swap out a rotor stator if you want to utilize that. We have some customers in the battery field that are using they're milling ball mite, and they're using rotor stator instead of a horizontal mill or a basket mill. Very, very good results, and very quick. So here is that that approach, that quick change system. So you see the basket mill on a stand, and then you have the dissolver on a stand, and you just go and swap out as you need to, depending on what part of the process you're in. So basically, one machine for everything, pre-dispersing and milling. And then here's one example where we actually have the machine running with the vacuum. So we are able to eliminate any foam. We're able to put in more energy. We have faster product transfer. Again, we can purge it with nitrogen or argon. And then there is a variety of different vacuum pumps available. And this is really designed for large-scale manufacturing. Then we have the 2-in-1 combo. So where you don't actually have to swap out anything. This is already a full unit incorporating the dissolver portion as well as the basket mill all in one. So you put your container there, you pre-disperse. When you reach the desired particle size and you want to mill your slurry, you just push a button on the control panel. And then at that point, you're now milling, and that will then give you the primary particle size that you need without having to move containers around, swapping parts or anything. Everything is on one machine. It's called the DISMAT TM. It's a 2-in-1 dissolver/basket mill combination. Also can be ordered in full ceramic and with the vacuum option. Same machine here, just kind of giving you some more details, what we just talked about. Really easy to scale up from the lab space, from the TML, what we talked earlier, to the TM. The upscale results are very, very good. We usually talk about a 15% increase in our dispersing or milling time from lab to manufacturing. So very, very good scalability. And again, the TM, that 2-in-1 is very, very nice. Gives you a lot of advantages. You buy one machine for both your pre-dispersing and milling. Easier to maintain, easier to clean, more space for other machines in your manufacturing arena. Here is a live example of two TM systems installed with 2,500 liter container on the left. You can see that the cowls blade have not been attached yet. They're behind the gentleman with the gray sweater. They're still leaning against the blue drum, but they would then pop on the bottom. And on the right, the same machine, except there it's lowered. That's what it would look like when you're actually processing your slurries. And then you push the button, and then the basket comes down, and now you're fully milling. That's what the basket looks like. Here we have basically the entry on top, where basically there is a pumping wheel is located right inside. That will actually create a vortex to draw the mill-based electrolyte into our basket, when then the milling disc and the media will do the milling. The media is added right here where you see that screw. You remove the screw, and then you take a funnel, and then you add the beads that way. And then on the bottom, we have a screen, and right below the screen, we have a cowls blade. So the cowls blade actually will draw your electrolyte or slurry out of the basket, then push it back around to the top, where then that vortex wheel inside of the mill will take over and suck the mill base back into the basket for a very good flow in and out of the basket to give you very, very good, efficient milling performance. And then here is a good drawing of the actual basket mill. So we can see the pumping wheel on top that creates that vortex. Right below is our milling disc. So that chamber would be filled with beads. They're not on that picture. We have really good cooling throughout the entire basket. And then we have a screen on the bottom, and right below that screen we have the cowl split to draw the mill base out of the basket. So the screen will keep the beads inside and not allow that the beads flow out and then they're inside of your slurry. So that's the design. Very efficient and excellent cooling properties. Here you can see this drawing, the mechanics. So the cowl's blade will draw the slurry out of the basket and then push it to the top, where then that vortex pumping wheel will create that vortex and suck it back in. So you have very good flow of your slurry in and out of the basket. So we have a few more slides. Just talking briefly, the vertical bead mill, that APS system I mentioned earlier, it's basically for lab scale and small pilot. So you have two containers. You have the top container filled with your slurry or electrolyte or separator coating. You add beads to the same vessel, and then you basically would mill the material. There is a cover that goes over it, so it's fully sealed. And when you are ready to purge your material, you remove a drain plug on the bottom. There's also a screen that's in there. And then you would hook up an air hose to our cover. There's a socket, and purge the material out of that container into a catch container below using air pressure. So it's a very efficient way of getting material out of the container into another vessel that has then the milled material. Unfortunately, not for large-scale production. This is really only something for lab scale or small pilot. Also very easy to clean compared to like a horizontal medium mill. Here we have just different control panel options. So that C technology panel we talked about earlier is on the left, giving you a lot of different pieces of information, very critical for upscale. Your RPM, the amount of energy you're putting in, our torque value in Newton meters, which is your viscosity measurement, the actual tip speed, so you don't have to calculate it, it's displayed already, your temperature, and the timer function. And then we have a standard amp controller giving you just speed, the amps in energy and temperature, no ability to store the data, but also very easy to use in a manufacturing environment because sometimes the operators don't want to mess with a lot of the technology. So this is a very simple way of producing the material. Here's a picture of our lab in Germany at VMA. It's there 30 miles outside of Cologne. So if you're ever over there and want to visit us, please, you're more than welcome. We can also run your materials for a trial. But we also have the same or similar capabilities in Wallingford at BYK USA. We have a laboratory up there that I run, and we have different types of equipment. We have horizontal medium mill. We also have a basket mill. We have vacuum systems, rotor, stator. We have all the right tools that are needed to develop a good battery slurry, and also help you, maybe point out exactly the right technology that will be suitable for your process. And because we are at BYK USA, we also have the advantage to leverage some of the synergies that we have with our colleagues on the additive side. So they make a number of additives that go into our cathode or anode or separator coatings, and they are the best people to speak to, but they will assist us if you come up for a trial to give us recommendations on the different types of additives to help you formulate your material or improve the formulations. So it's a Class A site. We have a clear development capability up there. We also are able to basically run trials on your product and then compare them. For example, you want to try a basket mill and you want to benchmark it against the horizontal medium mill. So we have that option. We also have the measurement technology to tell us exactly the results of our tests. And then you can make a better informed decision of what works for you and what type of equipment would be good. We can also have you come in just to look at the equipment without running an actual trial, or it could also be a training location if you want to send somebody up your company to learn more about the milling technology and the equipment, we can also offer that as well. That's it. Thank you very much. I appreciate your time today, and it took a little longer, but I'm opening up for questions.
Those were some really, really good slides that I think I saw a couple too that might be new that I hadn't seen. We do have a question. What is the relationship between the bead diameter and the minimum particle size that can be achieved? Any formula?
So there is not really a formula. So basically, what we do is we look at the type of obviously the slurry or the formulation, and we always start out with a 1 to 1.2 millimeter bead size when we are usually between around 10 microns, and that if we optimize everything, we're able to go down into the low micron range. I would say probably 1 to 2 microns. If you want to go below that, you need to use smaller beads, 0.6 to 0.8, and then progressively go down. I would say that for battery development, for the ceramic coatings, we really need to use 0.3 millimeter beads and a 0.1 millimeter screen to get us below 100 nanometers. But all formulas are not the same, and I cannot really give you an exact answer to. There is no exact table. So, but these are approximations, and everybody needs to kind of try that out for themselves. I hope that answers it.
We have another question here. Which dispersing equipment type do you suggest when dispersing NMC 811 as slurries? Do you see damage in the particles when dispersing?
I would have to talk to my colleagues. I'm not very familiar. I'm not a real chemist, so I would hate to speak to that. But if you would send me an email, I will definitely get back to you with a good answer.
There was a question about the title. I understand the dispersion and milling terms, but what does the term energy storage refer to?
Well, this was just basically a term we picked for using for that end use market battery. So, no specific reason. We have customers that use it to develop hydrogen fuel cell, the energizer, the coatings. We have it to develop the different battery slurries. So it was just something that was picked.
I hope that makes sense to everyone, and that's helpful.
But I would like to say one thing that's really important. The technology, the principle of dispersing and milling is the same. So this was not something that was reinvented here for the battery market. This is already good base knowledge, and the core principle of how we go about dispersing and milling is really the same. I mean, there are some differences in the types of equipment choices that are made with the materials and somehow in optimization parameters, but the equipment itself is really the same. I mean, we have some customers here that actually do basket milling under vacuum, which you don't really see when you develop standard coatings. They really don't want any air entrapment, so we have specific solutions there. But from a principle point of view, it's actually the same.
So a follow-up to that was, so these machines are used for materials other than paint?
Absolutely. So we have a lot of different end-use markets. If you go on our website, vma-getzmann.com, you can see all the different industries. It goes from battery development to pigment development, inks, 3D print media, also agricultural. They make different materials that go coatings for plants, pesticides. I mean, you name it. It's very versatile. We have companies that use the technology to develop 3D print media, for example, CBD lotions, cosmetics. I mean, we have all sorts of different end use customers.
And I think we could probably, one more question here. Which type of DISPERMAT equipment would you recommend to create inorganic pigment pastes for coatings?
That depends on the type of particle size. I mean, what you're looking for. But for example, we have in that arena a variety of customers that use the basket mill approach and also horizontal medium mill approach. So that depends really how small you go and what is the flowability of the material, the viscosity range. If the material flows really well and I don't need to go below 500 nanometers, then I will probably suggest you go with a basket mill setup. Also, if it fits the volume, I mean, 2,000 liters, I mean, you can't do really much more than that. If you have flow issues or you need smaller particle size than that, then a horizontal medium would probably be the better option.
Great.
But again, I would welcome if you would like to see the equipment and do a benchmark. We'll have you come up to Wallingford. We will not charge you for a day or two to run your material and kind of find out what technology really works best for your end use. So let us know, and we're more than welcome to accommodate you.
Yeah, please feel free if you receive an invitation on any of the webinars, you can reach out to us that way if you need to reach us or via our website. If you have an idea for a webinar that you'd like to do, please send us that information. Andy, you did a great job today as always, and we thank everybody for their time. And we will send out the recording of the webinar right after we get off.
And also one thing, these webinars are all uploaded to YouTube, so you can watch them at a later time. We already have a number of presentations up there. We also have our own YouTube channel where we have a video about our lab space and some of the presentations online. So please feel free to check it out. Thank you so much.